In the Pacific Islands, climate change has intensified droughts, increased soil salinity, and compromised freshwater supplies, undermining food systems by reducing large-scale producers' access to reliable agricultural-grade water. Vanuatu, a humid country reliant on rainwater and freshwater for agriculture, increasingly faces extreme temperatures and rising sea levels, posing a serious threat to its agricultural industry, which makes up 25% of GDP. This is especially evident during El Niño seasons, when rising sea levels cause saltwater intrusion that increases salinization of irrigation water and soil. This severely limits access to reliable farming water and is devastating for subsistence and homesteading producers who rely on consistent irrigation and freshwater to sustain their farms and communities. Sweet potato and taro, two Pacific agricultural staples, are particularly vulnerable as their growth depends on irrigated conditions and high water availability. In fact, the last El Niño season saw yields fall by 24%, affecting nearly 100,000 people. This leaves farmers and communities vulnerable to crop failures and food shortages, significantly diminishing climate resilience and increasing hunger and malnutrition. Currently, there lacks a sustainable, affordable, and locally adaptable water capture solution suited to low-resource island contexts. Our solution is the HydroWeb, a low-tech, sustainable, and scalable water harvesting system designed for the Pacific. Inspired by a 2016 study on an atmospheric water harvesting using hydrophilic surfaces and mesh structures to capture water from the air, we sought to recreate its function for low-income Pacific Islander farming communities, replacing costly high-end materials like copper mesh and silica gel with low-cost, locally available alternatives, namely recycled fishing nets, breadfruit starch-based, and a bamboo frame. It's easy to assemble, as farmers can simply follow the YouTube tutorial or our open-source guide and install the contraption on open farmland. By leveraging the Pacific's hot, humid climate, HydroWeb provides a clean, reliable agricultural water source without the need for electricity or complex and expensive infrastructure. It is estimated that 12,800 trillion litres of renewable water are available in the atmosphere in the form of water vapour that can be extracted through atmospheric water generation, making the HydroWeb an effective solution to freshwater shortages prominent in the region. Here's how HydroWeb works. Local farmers collect old fishing nets, plastic tubs or jugs, bamboo, and breadfruit peels. Machetes are used to cut and strip the bamboo, which is highly abundant and sustainable given its fast regeneration rates. Fishing nets are easy to source too, as many Pacific Island nations have highly active fishing communities. The fishing net is stretched between the two bamboo poles and secured with twine or dried straw. Breadfruit peels are boiled into a paste with water, producing a hydrophilic coating that is applied to the net. Similar to the surfactant on a spider's web, the nanocellulose in the breadfruit acts as a glue for the water, enhancing condensation and reducing wind-driven water loss. Breadfruit itself is ubiquitous in the Pacific, with each tree yielding 60 to 150 fruits annually. Yet peels are usually discarded, making them an ideal and sustainable, accessible material. Finally, a recycled plastic sheet or trough is attached to the base as a catchment. As air flows through the net, humidity condenses on the sticky surface. These droplets drip down into the catchment, feeding water to a jug or tub below. It's modular and can scale across hectares, making it viable for larger scale producers of staple crops like taro and sweet potato. Everything is open source, with YouTube tutorials, infographics, and printable instructions. We also train local builders to teach others, ensuring the effective dissemination of the design. It is estimated that HydroWeb can collect up to 1 litre of water per hour in 70% humidity, with even greater rates in the Pacific Islands, where humidity often exceeds 80%, making HydroWeb a highly effective rainfall-independent freshwater source. Designed for low resource settings, it upcycles marine waste and uses abundant, fast-regenerating local resources like bamboo and breadfruit, reducing raw material costs whilst ensuring long-term sustainability. Its zero waste, zero electricity and low-tech design eliminates production and maintenance costs, making it virtually free for households and farmers in low and middle-income countries. The open-source design, in conjunction with 100% locally sourced components, also enables the rapid implementation and scaling across the Asia-Pacific. The visual format of the tutorial also bypasses language barriers, ensuring effective dissemination of knowledge between different cultures. Assembly is completely DIY and community-led, requiring no technical expertise or industrial infrastructure. We'll start with a pilot program in Vanuatu, a Pacific nation facing acute water stress. From there, we aim to expand across the climate-vulnerable island nations using a community-led distribution model. By harnessing Pacific Island nations' natural climates and high humidity, HydroWeb provides a reliable, uncontaminated water source for larger farms and families in low to middle income countries, aiming to boost climate resilience in subsistence and irrigation farming. It is especially encouraged to be installed alongside taro and sweet potato plots, which account for over 50% of staple foods in the Pacific, but are highly vulnerable to water shortages. This directly addresses the Sustainable Development Goal 2, end hunger, promote food security, and sustainable agriculture. HydroWeb simultaneously improves food security and yields, while empowering communities to build resilience against climate-driven freshwater shortages. HydroWeb is more than a tool. It's a climate-smart, community-powered innovation. By turning discarded waste into life-giving water, we help farmers adapt to a drier future, climate-proofing agricultural water sources as temperatures soar and salinity increases.